overview. I'm going to give you a schematic of the system, that way you know something about the background of the system. Then we'll go into the results of the steady state and operating curve. Then I'll show you some of the results from the step functions, and then we'll end with some conclusions. This is a pressure schematic of our system, and basically it's set up for a paint booth. There's 3 separate booths, and here at the air inlet, this is the motor for our system, and it's a variable speed motor, which means you can put different inputs into it and powers a fan, which pressurizes these booths. So you can set each booth to the pressure that you like for painting different objects, or different pressures that you need. The input is specified by the user in the LabVIEW interface, and the output is the air pressure resulting from the motor's response. So you only have one variable, which is what you input into the engine, which is a percentage of the power. And then the output comes in, is measured in centimeters of H2O, which is pressure. This is an example of one of the experiments that we ran. This particular experiment was at 50% input, and this shows the output of the system. From 0 to 5, the motor was building up pressure, and then once it hit steady state at around 5 seconds, we took this as the range of the values and got the average, which was 17.7, and had an uncertainty of plus or minus 0.61 centimeters for H2O, which is the pressure. The whole experiment took about 20 seconds. And we did this experiment for different inputs, and then this value here we used to make our steady state operating curve, which pretty much linked the average pressure that was achieved by that input at different inputs, and it resulted in our steady state operating curve. This is the output, which was our steady state operating curve, and as you can see, from 70%, from around 65 to 85%, it goes close to linear. So we set this up as our operating range. That's where the motor wanted to be at. It was most predictable in this range. There wasn't as much uncertainty. This was an example of the step function. In the step function for this particular trial, we run it from 65% was the input, and then there was a step up of 15% power. From this data, we can calculate what the dead time was T0, and it was 0.1 seconds for most of the inputs. We got 0.1 seconds. They were responded very quick, so it made it hard to measure. The tau value for this particular was 1.6 seconds, and what that is 63% of the time that it took to reach steady state after the step. The K value, which was the gain, is the change in C divided by the change in N for this system. This is an example of the step down, and the values are calculated the same way, except we started with a higher input, and then we decreased the input, and all the values were calculated the exact same way. These are the averages of the tau, the K, and the T naughts with the uncertainties in there. At the lower ranges, the uncertainties were higher. And I'm not sure if that's because there's still a change in the pressure. It's not at a steady state, so the uncertainties are going to be higher. But once, like for the second range and the third range, there was no uncertainties, for example, for the tau. And then here, for tau, you can see that the uncertainty was higher than the overall range. So these values at the range 3 and the operating range, they're going to be better. And in conclusion, understanding the steady state operating range of the system allows the user to predict the output pressure. So when someone's painting in that paint booth, they want to stay in the the operating range of the engine. That way they can better predict the outcome inside the booth. And through that steady state curve that we developed, we were able to identify where these ranges were for the engine. And when the system is ran outside that range, it tends to vary. So if you were to run at a lower input, it's not as predictable what your pressure will be inside the tank. And that concludes the presentation.